Hello, everybody. Welcome to our critical design review for Group 12 on Solaris, the solar optimized land autonomous recharge and intelligence system. My name is Ryan Markwitz. I am a computer engineer and I am the software lead for Solaris.
My name is Raphael Puig. I am an electrical engineer and I am the power lead on Solaris.
I'm Nathan Hammond, and I'm an electrical engineer, and I'm the PCB design lead on Solaris.
My name is Garrett. I am a computer engineer, and I am the hardware and software integration lead for Solaris.
Now time for a quick background on why we made Solaris. A normal solar panel is passive. If it ends up in shade, it just loses power and stays there. Most basic setups also don't let you charge a device straight off a USB-A, and they don't tell you anything about how much energy you're actually pulling in. What we wanted to do was make the panel move and make it talk to you. Solaris notices when it's sitting in shade and drives itself to a better spot, so for a full day you can collect more energy than a fixed panel would. It has a USB-A output so you can charge things directly off of it, and it sends live data to a phone app over Bluetooth Low Energy so you can see things such as battery level, net power gains, and other telemetry of that sort.
On to our project goals and objectives, we've categorized our functional targets into two tiers, that being basic and advanced. To start with the basic goals, we kind of identify our foundational requirements, which is to design a system capable of rotating the solar panel across two axes, that being pan and tilt. To interface this with hardware, we create a dedicated phone app that will serve as the primary means of communication between the user and the robot. And using this Bluetooth Low Energy link, the system will measure and report critical telemetry information back to the end user. The project gets a bit more complex when we move to our advanced goals, where the core directive of Solaris is identified as the robot being capable of autonomously moving out of shade on flat ground and navigating into a highly luminous area. This means that the firmware and the hardware must be optimized so that the energy gained from the moving robot is strictly greater than the energy used by the motors during runtime. Once deployed, we will ensure that the system can operate completely autonomously without any external power or physical user input. To support this deployment, the robot must accurately avoid collisions autonomously. And given that, we want to provide a little bit of operational flexibility. So we provide the user with the phone app about 3 different operational modes, that being a stationary, a manual, and then of course the internal autonomous mode. So to underpin all these features, we will integrate advanced motion sensing to precisely quantify the distance traveled during movement operations, and we want to design the electronics and firmware architecture with strict modularity in mind so that we can ensure that the system is robust and scalable. Moving forward from our high-level objectives and goals, we take a look at the more concrete engineering specifications that drive our design decisions. So looking first at the overall system, our primary deliverable to the end user is usable power. So after a sunny day of optimal tracking, Solaris is required to provide the user with at least 15 watt-hours of usable energy directly from the battery. For mobility across various terrains, we target a standard operating speed of 0.3 meters per second in both forward and reverse directions. To achieve our core directive of optimal solar tracking, the mechanical assembly requires a continuous 360-degree range of motion on the pan axis, and this is also paired with a 30-degree range of motion on the tilt axis. To ensure the system remains somewhat portable and manageable to deploy, we establish a strict total weight limit of around 50 pounds or less for the actual fully assembled robot. To meet system level constraints, our solar panel hardware must natively support the minimum 15 watt-hour day generation target, and we back this up with a battery capacity of 256 watt-hours, which gives us a massive energy buffer for autonomous operations and user charging even during prolonged periods of low light. For communication, our Bluetooth Low Energy module is rated for an effective wireless range of 1 to 6 meters, and this ensures a stable, low latency connection for our user controlling the robot nearby. Lastly, to move a near 50-pound chassis at 0.3 meters per second, our drive system relies on geared brushed DC motors, capable of outputting between 18.14 and 24.5 newton meters of torque.
This is our hardware block diagram consisting of 3 systems: external, internal, and remote.
Now we will go into the technology and part selection of our 5 subsystems, each with their own deep dive, and we will go in order of control, drivetrain, solar tracking, power, and then last, communications.
For electronic selection, I'll walk you through the process of our microcontroller selection for a system like Solaris. We benchmarked 4 different candidates, which is the STM32U0, the MSP430FR6989, and 2 espressive chips, the ESP32S3 and the newer ESP32P4. As you can see, the MSP430 and the STM32 chip, while highly power efficient, they lack any integrated wireless capability, which would necessitate an external radio module and complicate our hardware footprint with SPI and UART bus layout. On the other end of the spectrum, the ESP32P4 offers massive processing capabilities, but has the same issue. We ultimately select the ESP32 because it utilizes a dual-core architecture, hits every target metric perfectly, and with the integrated Bluetooth Low Energy and Wi-Fi, and a dense grid of 45 GPIO providing ample routing flexibility, with dual 12-bit ADCs across 20 channels, and a highly competitive price point of $6.76 per unit, it offers everything that we're asking for our project and makes for easy implementation.
The motor selection process for Solaris began by evaluating AC and DC motor technologies. While AC motors offer excellent efficiency and long-term reliability, they require additional power conversion hardware, which increases the system size, weight, cost, and complexity. DC motors are directly compatible with the robot's 12-volt battery system and provide strong, low-speed torque, making them more suitable for outdoor terrain and battery-powered operation. The next decision was between brushed and brushless DC motors. Brushless motors provide higher efficiency, longer lifespan, and more advanced control capabilities, but they require dedicated controllers and more complex integration. Because Solaris operates in short bursts and prioritizes simplicity, reliability, and ease of implementation, brushed DC motors were determined to be the more practical solution. Their straightforward control methods, predictable operation, and reduced integration complexity allowed the design to meet all performance requirements while minimizing development risk. After selecting brushed DC motors, a few different motor candidates were evaluated based on torque capability, operating speed, encoder availability, gearbox design, documentation quality, and ease of integration. The stepper-on-line motor offered the highest torque and a robust design, but lacked an integrated encoder, which could have increased the wiring and control complexity. The ES motor provided encoder feedback and sufficient performance for the application, but had less available documentation and community support. The GoBuilda motor offered the best overall balance of performance and practicality, combining sufficient torque for grass traversal, a 60 RPM output speed that matched the design requirement, an encoder, and a durable planetary gearbox. Additionally, its extensive documentation and widespread use in robotics applications reduced the implementation risk. For this reason, the GoBuilda motor was selected for the drivetrain.
For our solar panel, I compared monocrystalline, polycrystalline, and thin-film solar panel technologies. I chose monocrystalline mainly because it has the highest power generated per area than either of the other silicons. Since our project requires mobility, minimizing the area and weight of the solar panel was a top priority. I chose the MPA 20S-12J solar panel because it had the highest power density compared to any other solar panel I could find, and it also has a very low weight of only 3.16 pounds.
Now I will be going over the light sensor technology selection for Solaris. This is how we sense light, and it does two jobs: deciding which way to drive out of the shade and pointing the panel at the sun. We only need to know which side is brighter, not exact lux, so we chose phototransistors. They have built-in gain, so one resistor gives a usable signal with no amplifier like a photodiode would need. A published study also showed that there was about a measured 40% more signal than LDRs, and they're easier to implement than I2C parts since 4 identical I2C sensors can run into addressing problems. For us, it's just an analog read. After choosing phototransistors for the technology selection, there are about 4 phototransistors that made the most amount of sense for Solaris. For the actual part, we picked the TEP 5600. Its 20-degree viewing angle is narrow, which gives sharper contrast between the lit and shaded sides, and the contrast is the signal we track on. It responds to the visible range, so sunlight doesn't get skewed by infrared, and it's through-hole, so we can mount it on the chassis of the robot.
The charge controller interfaces our solar panel with the battery and the load of Solaris. I selected the multi-power point tracker technology because it can transfer the maximum power output of the solar panel, resulting in a higher energy capture over the course of a day than the PWM controller. I chose the Jenison GV5 lithium iron phosphate charge controller. It has a low operating power consumption, which minimizes wasted power through the controller, and it also has a small form factor which will decrease the added weight to the robot and make it easier to integrate. For our battery technology selection, I compared lithium-ion, lithium iron phosphate, and lead acid. We chose lithium iron phosphate because it has a significantly higher specific energy than lead acid and is also much more stable and safe to use than lithium ion, especially for our applications involving charging of the battery via the solar panel. I chose the Renogy 20 amp hour 12.8 volt lithium iron phosphate battery. It has one of the highest operating temperature ranges and also is low cost.
This slide compares the two primary voltage regulation technologies considered for Solaris, linear regulators and switching regulators. While linear regulators offer lower complexity, their efficiency decreases as the voltage drop across the regulator increases, resulting in greater power dissipation. Because Solaris operates from a battery-powered system and requires both 5-volt and 3.3-volt rails, efficiency and thermal performance were prioritized. For these reasons, switching regulators were selected due to their higher efficiency and reduced thermal losses. This slide compares the switching regulators considered for implementation within Solaris. Selection criteria included efficiency, output current capability, implementation complexity, cost, and reliability. The LM2679 was ultimately selected due to its 5-amp current capability, straightforward implementation, and established reliability. Additionally, the same regulator family could be used for both the 5-volt and 3.3-volt rails, simplifying the overall design and implementation.
For our energy monitoring IC, we chose the INA228 for its high fidelity and ability to perform on-chip energy accumulation calculations.
Now I'll be covering the ultrasonic sensor selection for Solaris. This sensor is for crash avoidance. We're running 4 of them, 2 facing forward and 2 facing back, mounted at the corners of the robot. We did the geometry on beam angle and sensor offset beforehand, and what fell out of that was a target beam angle in the 40 to 45 degree range with about a 10 degree offset on each sensor. That kept the blind spots in front of the robot manageable while still leaving good room to turn. Working from that, we picked the MB120.
Quantify our distance travel, track orientation during steering adjustments, and calculate absolute heading adjustments. We evaluated 3 inertial measurement units, the Adafruit BNO085, the MPU 6050, and the ICM 20948. The MPU 6050 was quickly ruled out because it only offers 6 degrees of freedom. The BNO085 is an outstanding 9 degrees of freedom sensor featuring a built-in ARM Cortex processor, which is dedicated to running full on-board sensor fusion algorithms, but due to its price tag and its rigid SH2 protocol wrapper, which adds a software layer overhead that we just wanted to avoid. The final choice, of course, is the ICM 20948, and it provides a complete 9 degrees of freedom solution, which integrates the 3-axis accelerometer, gyroscope, and magnetometer at a highly effective $1995 price point. Features an advanced digital motion processor, and it supports a standard I2C and SPI bus, while boasting incredibly low power consumption modes, and it provides the exact balance of relative compass stability and direct register access needed for our navigation stack.
So this is the software stack behind the phone app for Solaris. For the front end, we're using React Native instead of SwiftUI or Flutter. The main reason is it builds for both iOS and Android off one code base, and our team already has React experience. This makes the learning curve a lot shorter than picking up Swift or Dart in a couple semesters. For the BLE side, React Native pairs with an NPM package called React Native BLE PLX, which handles scanning, connecting, reading, and writing characteristics, so it covers what we need to talk to the robot. The backend is FastAPI written in Python. We looked at Django, Spring Boot, and Express, but FastAPI is built for exactly this kind of lightweight API layer, and we've used it before, and it also pairs cleanly with Postgres. The database is PostgreSQL, and it's hosted on Supabase. Our authentication is handled through Clerk, so we didn't have to build sign-in from scratch. Now I'll cover the wireless protocol selection for Solaris. This is how the phone and robot actually talk. We compared Wi-Fi, Bluetooth Classic, BLE, LoRa, and Zigbee, and eventually we went with Bluetooth Low Energy. The biggest reason is that it connects straight to a phone with nothing in between. LoRa and Zigbee have great range and great power numbers, but a phone can't connect to either of them directly. You need a separate hub or gateway, and that's the extra hardware and setup we didn't want for a simple one-to-one link. So realistically, it only came down to two choices: Wi-Fi and Bluetooth. BLE matches exactly what we're sending, which is low-rate telemetry and short control commands, so we're not paying for a bandwidth that we're not using. It draws less power than Wi-Fi or Bluetooth Classic, which matters on a solar system. It's also well supported in mobile development, so it kept the app simpler. The one trade-off is range. BLE doesn't have as much range as Wi-Fi, but since the robot is meant to be controlled by someone standing nearby, we were okay accepting that limitation.
For our embedded stack, which is going to complement our firmware architecture, we looked at Espressif's ESP-IDF, Arduino, of course, and Platform IO as an add-on for VS Code. Now, functionally, ESP-IDF and Platform IO are no different, and therefore, for our application, we use both interchangeably, whereas Arduino IDE is too abstract for our use case and doesn't take full advantage of the ESP32S3's environment.
This slide shows the ESP32 section of the Solaris main PCB. One of the primary design goals here was modularity. To reduce routing complexity and simplify development, several subsystems were implemented as separate daughter boards, including the motor driver boards, voltage regulator boards, and light sensor boards. This allowed individual subsystems to be independently tested and validated before the full system integration. Several standard design practices were incorporated to improve reliability and simplify hardware bring-up. Local decoupling capacitors replaced near critical power inputs to improve voltage stability. The dedicated enable... It's never happening. This slide shows the core architecture of the Solaris main PCB, that being the ESP32. One of the primary design goals going in was modularity. To reduce routing complexity and simplify development, several subsystems were implemented as separate daughter boards, including the motor driver boards, voltage regulator boards, and light sensor boards. This allowed individual subsystems to be independently tested and validated before full system integration. Several standard design practices were incorporated to improve reliability and simplify hardware bring-up. Local decoupling capacitors replaced near critical power inputs to improve voltage stability. Dedicated enable and reset circuitry was included to support reliable startup and programming, and onboard LEDs and push buttons were added to assist with testing and debugging throughout development. This slide shows the primary sensor and subsystem interfaces used throughout Solaris. These include the phototransistor array, ultrasonic sensors, IMU, wheel encoders, and energy monitoring circuitry. Given the number of required sensors, multiplexers were incorporated into both the light sensing and ultrasonic sensing systems to manage the available I/O resources. Additional design considerations included 100 ohm series I2C signal integrity resistors for the IMU, and the use of connectorized interfaces to simplify integration and testing. Overall, this portion of the design focuses on efficiently interfacing the required sensing and feedback systems while maintaining a modular architecture. This slide shows the USB to UART programming interface we used on Solaris. The CP2104 was selected over the 2102 due to its additional functionality while requiring minimal additional implementation complexity. ESD protection was incorporated on the USB interface to improve robustness, and the remaining support circuitry follows the manufacturer's recommended design guidelines. This slide shows the 30 amp motor driver subsystem used throughout Solaris. The VNH 5019 was selected due to its ability to handle the stall current of the motor that we selected. Several design considerations were incorporated to support reliable operation. A dual optocoupler was added between the control signals and the motor driver circuitry to provide isolation for the PWM and directional signals, while reducing the impact of motor-generated electrical noise on the main PCB. A custom direction control implementation was also used to reduce the number of required microcontroller I/O signals, with the trade-off being the loss of active braking functionality. Noise suppression capacitors were added across the motor output terminals to help mitigate switching transients and reduce conducted noise generated by the brushed DC motors.
For our energy monitor, we have a 4-terminal sensing resistor in series between the battery and the load and charge controller. Our IC reads the voltage differential across the resistor and sends energy data over I2C lines to the MCU. Our light sensor measures the current going through the phototransistor by measuring the voltage across a 10K shunt resistor. For the 3.3 and 5 volt voltage regulators, I used Webench to design the circuit. The main difference between the two voltage regulators are the feedback resistors. I included a button test circuit on the same voltage regulator schematic to verify that the circuit is outputting close to the right voltage. Here is the 5 volt voltage regulator. This is a CAD model of what our Solaris chassis will look like. The main features are the dual-axis solar panel mount system and the all-terrain wheels.
This slide shows the final layout of the Solaris main PCB. The primary challenge during layout was accommodating the large number of peripheral connections while maintaining clean routing and adhering to project design constraints. Particular attention was given to ensuring all peripherals could be successfully routed, placing bypass capacitors as close as possible to their associated power pins, and minimizing I2C trace lengths while reducing unnecessary trace crossover. Connector placement was also coordinated with the mechanical design to simplify subsystem integration and cable routing. The final layout successfully met all routing requirements while maintaining accessibility for the various daughter boards and sensor interfaces used throughout the system. This slide shows the final layout of the motor driver daughter board. Because this subsystem handles the highest currents in the system, particular attention was given to power distribution and component placement during layout. Current carrying traces of 80 mils were sized based on the expected operating current of the selected motors. While polygon pores were initially considered, analysis showed that they were unnecessary for the anticipated load conditions, allowing routing to be simplified while still meeting current carrying requirements. Bypass and filtering capacitors were placed as close as possible to the motor driver IC to improve supply stability and reduce switching noise. The dual-channel optocoupler was positioned near the control interface to improve isolation between the motor circuitry and the main control system. Component placement was also arranged to maintain short power paths and simplify integration with the main PCB.
For our voltage regulator PCB, we positioned all components in the same orientation to help with surface-mounted soldering. For our light sensor PCB, we opted for a small board layout to allow easier placement for 8 of these boards throughout Solaris. On the energy monitor PCB, we chose wide-width power traces to allow for a max continuous current of 5.3 amps in our system. We placed our connectors on the edges of the board for easier access, and in this image you can clearly see the 4-terminal sensing resistor pads we will be using at the center of the board.
For consistent behavior across our entire system, we've designed a functional state machine matrix which maps out our software backbone, and this is broken down into 5 distinct categories. To start with connectivity, at boot, if no mobile app client is paired, the ESP32 enters an active advertising mode, giving visual feedback via like a blinking onboard LED. Once a pairing handshake has occurred, a system switches to standby and a formal mode command begins. So then we move to our control mode, where depending on this packet that we can receive from the phone app, the system branches. In manual, it spins up a listener loop. In stationary, it enters localized hibernation, and in auto, we enter our custom autonomous motion. Now, moving to the autonomous mode, the robot assesses time and proximity. If it's night, it enters deep sleep to preserve battery. During the day, if the 4 ultrasonic sensors detect an object closer than 20 centimeters, it triggers the obstacle avoidance state, stopping forward travel and executing a pivot maneuver until real-time data can be assessed. And if the path is clear, it advances to goal evaluation. Now in goal evaluation, we can read our phototransistor array. If the light differential is below our threshold, meaning we're in a shadow, the robot triggers a wandering pattern to hunt for high luminosity zones. Once the light reading surpasses our target threshold, we can execute solar alignment where the drive motors are stopped and we engage the pan tilt motors to lock onto peak sunlight. Upon the successful alignment, we can enter hibernation and the main systems will charge. Now, finally, we find our way to the safety system, which runs continuously at a high priority and handles the system exceptions. So if the battery drops below 10%, or if we find that the wheel encoders indicate the robot is physically jammed, we can trigger a critical stop, which kills all the power to the motors and shoots an emergency error packet back to the app client. And then below that, we have a working example of some of the information that gets sent back and forth between the ESP32 and the mobile client.
Here's the project status for Solaris. For parts acquisition and design, we left them at 99% as opposed to 100, because even though they're complete, we wanted a 1% headroom in case we need to make slight alterations to the design or get a different part. For prototyping, we left it at 40%. Every single individual component has been tested, but the full integration hasn't been done yet, so we left it at 40%. For the coding, we said it's about 60% complete, since the phone app is completely 100% done, and all the individual components have been tested. So all that's left to do is just the code for the final integration. Here is a quick look at our phone app for Solaris. So you can see the landing page on the left, a sign-in screen in the middle, and then on the right you can see what the user would see, the telemetry data that they can swipe through and look at different times, different days, as well as the mode change, so they can change it between stationary, automatic, manual, and in manual mode you can send steering and throttle information.
On this slide, we have some examples of the prototyping that was done via dev kits for Project Solaris for all main subsystems. So the energy monitoring unit, the ultrasonics, the light sensors with the phototransistors, and the motors via encoder usage. And all these images are representative of testing our pin layouts that would be used with our main schematics for the PCB fabrication. At the bill of materials, where we take a look at the way money was spent on the project. So we see some pretty large price points for the motor expenditure, the chassis, and then for miscellaneous components. Now, miscellaneous components encompasses any dev kits purchases that were not itemized, as well as any components that were going on the PCBs once we purchased them. So a big key consideration with the project was always robustness and reliability over cost.